to the linear and generalised linear models course. So the module, as it indicates, will cover linear and generalised linear models. So if you've got the notes, chapters 1 and 2 are on linear models, and after that, chapters 3 to 7 are on generalised linear models. Okay? You may be taking this module under one of 3 different codes, and the arrangements for things like assessment are different depending on which code you're taking the module under. So, third year students will be taking it as MAS6003, fourth year students as MAS6003, MSc students will be taking it as MAS6003. Note that MAS6003 is a module which runs over both semesters, so this is only the first half of MAS6003. If you're taking the MAS6003, it continues into the second semester with further lectures. Okay? So that's all extended linear models, and that will be taught by Professor Wilkins. Okay, so as I said, there are 2 main sections, so one on the linear model, general standard linear model, and that's in chapters 1 and 2. You may find that quite a bit of the material in chapter 1 you've seen a bit of before, so some of chapter 1 will be revision for some of you, but certainly I don't expect it to be revision for everybody. Chapter 2 extends the theory a little bit more, and particularly is about checking what to do when some of the assumptions that we make for the standard linear model do not hold, and whether they hold or not, and what to do if it turns out that they do not hold. If people want to move into the centre a bit, so there's room for people who are coming in slightly late, I can see there are a few seats in the middle, but none more to the edge. Okay, so then chapters 3 to 7 introduce generalised linear models. So generalised linear models are a family of techniques which we use for frameworks where the general linear, the standard linear model does not work. So the assumptions that we want to have for a standard linear model simply cannot be justified. There's this family of techniques for which we call generalised linear models, and sections 3 to 7 introduce those. Okay, so specifically the general framework is covered in chapter 3, and then chapters 4 to 7 cover various specific examples of techniques which are in that family. Okay, assessment for the module. So if you're taking MAS367, there is simply a standard 2-hour exam, and this is held in the January-February exam period. If you're taking MAS467, then you take an exam which is the same as the one for MAS367, but in addition to make the difference in the 3rd year and the 4th year module, there's a project which will be on the generalised linear models material later in the semester, and so the deadline in that is in December, and it's worth 30% of the module mark. MSc students, you have an exam at the end of the year. That covers the whole module, so it covers both the semester 1 material, which I'm covering, and the semester 2 material, which Professor Wilkinson is covering. There's also a project as part of the assessment of that module, but that's on the semester 2 material. Okay, because it's the easiest place to get everybody together with access to, the course material will be on MOL. We'll also have discussion boards, and some of the assignment submission will be also via MOL. So I'll use the discussion boards for announcements and discussions. You can post queries there as well, and I'll also post a general update on how far we've got. That's to a large extent for the benefit of distance learners. So we've got several distance learners who are taking this module, but obviously they're not here in Sheffield. So they will be watching the lecture videos, which is why we have the microphone equipment and somebody recording it at the back. The discussion boards are particularly useful for them, but they can also be useful for everybody in here as well if you've got any questions about what's going on in the material so far. Okay, in the MOL system, it's possible to go into an individual discussion board, and there should be a button which says subscribe. If you press that subscribe button, you will get an email whenever somebody makes a post in the discussion board. So if you want to keep in touch with what's happening in the module and discussions that people are having by email, then subscribing to that, to the discussion boards, is a good way of doing that. A little bit about feedback and exercises. There are 3 sets of exercises. The dates for handing them in are built around the MSc timetable, and so they're handed in weeks 4, 7 and 10. I will put the first set of exercises on MOL fairly soon. So I'll mark them, the marking is for feedback, it doesn't count towards the overall module. If you want to contact me, my email address is there. My office is I9 in the Hicks building. Okay. Has anybody not managed to get an exercise booklet as they've been passing around? Okay, one more thing to say about arrangements for the course. So the other lecture will be on Fridays. I'm afraid it's at 5 o'clock. The timetable had to be changed at fairly late notice because of the number of students taking the module. It's in Lecture Theatre 7, so some early versions of the timetable said Lecture Theatre 5. It's now going to be in Lecture Theatre 7, which fortunately is not very far from Lecture Theatre 5, but I'm telling you now it will be in Lecture Theatre 7 tomorrow at 5 o'clock. Okay. So I'm now going to start off with the course material. And so we're starting off in section 1. So section 1 is about the linear model. As I say, some of what you see in this section may be revision for you. May also not be, and I'm trying to present it in a way that if you haven't seen it before, you can understand what's going on. Okay, so here is an example of a data set for which we might be interested in studying with something like a linear model. So this is only the first 5 lines of the data set. There's actually data on 305 patients in this data set. So at the moment these column headings may seem a little bit opaque. I'll explain what they are as I go through the slides. So you'll see the last 4 of them have simple looking numbers, often 0 or 1. And the ones over here have numbers which look like they're measurements of something. Okay? So where we've got 0 or 1, for example, the smoke heading, you can probably guess that 1 in that column means that that patient is a smoker, and 0 means that that patient is not a smoker. And you can guess similar things for the other columns there. Okay, so here now are the explanations of the column headings. So the first column, headed bold, that was the volume of air that the patient expelled when breathing out. Okay, so each patient in the data set was given a task to do which involved testing how much air they could breathe out. Okay, so high values of this suggest a respiratory system in good health, for example. Okay. Then the next three columns, EXA, gave the number of hours of exercise that that patient did per month. Okay? Pulse gave their scaled resting pulse rate. The one-headed pole, that's actually their lifetime exposure to air pollution. And then the other four columns, so these are the ones that had integers in them. Asbestos is, have they been exposed to asbestos or not? And as you might expect, 1 means that they have, 0 means that they haven't. Smoke, as I already explained, 1 means that they're a smoker, have they ever smoked in fact, 0 means they haven't. 1 is for asthma, 1 is, yes, they do have asthma, 0 is that they don't, and 1 which is probably the most opaque of them all, actually, when you first see the table, home, the numbers correspond to the different parts of the UK, so 1 is England and so on. So home is place of residence. Now, in the version of the notes that were printed out, there's an obvious typo that 2 of these headings have been swapped. So asbestos, and it's asbestos was swapped with home. So asbestos should indeed be, has the individual been exposed to asbestos, and home should be place of residence. So that was an obvious typo in the printed version of the notes. Okay, so what might you want to do? So, as I said, the experiment was measuring the volume that the patient produced. These 7 things are all things that we think might possibly influence the health of somebody's respiratory system. Well, possibly not this one, but certainly the others we might expect to influence the health of somebody's respiratory system. So, amount of exercise, their pulse rate, exposure to air pollution or asbestos or smoking, and whether they have an underlying medical condition like asthma. Okay. So what we're interested in is how do these 7 variables, other than the one that's been measured in the experiment, influence the result of the experiment. That's the sort of question that we'd be interested in asking. Okay, so how does the volume of air that the patient expels relate to those other variables? Okay, so I wanted to emphasise that there are several different types of variables in the data set. And the type of variable that a variable is often influences how we handle it in our statistical procedures. So the first 4 variables in the table, the volume expelled, the number of hours exercise, the pulse rate, and the pollution exposure, those are continuous variables. They're always measured with some real number. If we're modelling them, we would think of them as continuous random variables. Okay? The others are very different. The others are categories, or sets of categories, rather. So in 3 cases, asbestos, smoke, and asthma, it's simply yes or no. Does this apply or does it not apply? Okay? So for the smoking one, have they ever smoked? In that case it says 1, but if they haven't ever smoked, then it says 0. So these are variables where each observation is put into a particular category. So they're often called categorical variables. Later in the course, we'll usually call them factor variables. Okay, so home had 4 different categories that we were putting the observations into, corresponding to England, Scotland, Wales, and Northern Ireland. And the others just had 2 categories, so they were binary. Okay, so just go back up again and look at the table. You can see that these 4 are the factor variables where the categories have been labelled essentially arbitrarily. We could use different numbers here. In particular, for this home thing, we could have a different association of the numbers to the different parts of the UK. The numbers really make sense in some units or other. They are a natural way of thinking about the measurements that we've taken. Okay, so what are we trying to predict? We're trying to predict this volume of air expelled. So that number is what we call the response variable. So vol, the first number in the table, that is what we call the response. Sometimes also called the independent variable. There are quite a few, sorry, the dependent variable. There are quite a few different names for things that float around in this subject. So response variable or dependent variable would be common names for the thing we're trying to predict. In this case, the volume variable. Okay, so in this example, the response is that first column vol. So the other variables are ones that we're using to try and predict the response. So those are called independent variables, predictor variables, or explanatory variables. Okay, so perhaps these ones are particularly clear, the meaning, in terms of the fact we're using them to try to predict the response of the other variable, or to explain the values of the other variable. Okay, so there are various questions that we might like to ask when we have this sort of situation. So one question is, do we actually need all 7 of our potential explanatory variables to give a good prediction of the response variable, the volume of air expelled? So we could ask, which of those 7 variables are best at predicting the volume of air expelled, or another way of thinking about it, explaining the variation in the volume of air expelled. Okay? And straightforward question, do we need all the variables? For example, do we need the exposure to pollution? Do we need which part of the UK they live in? Okay? So this process is essentially we're choosing a model for our data, which ones of the potential explanatory variables actually are useful explanatory variables. Okay. Another question, which is slightly different, is how much of the variation in the volume of air the patient expels can be predicted with our model. So how much leftover variation is there which isn't explained by our possible explanatory variables? So we might well expect that there are some other features of the patient. So for example, there could be genetic factors which aren't covered by the 7 potential explanatory variables we had. How much of the variation that we find in our data set is actually connected with those explanatory variables which we have, and how much is actually potentially explained by other things we don't know about, can be modelled as completely random, or whatever. Okay? So that's another question that we might want to ask. How good is our model at actually explaining variation in the data? Okay. The linear models that we're going to have some assumptions. And the quality of a linear model at producing answers to the first 2 questions is only going to be valid if these assumptions are satisfied. Some of them are more important than others, and I'll explain a little bit more about that when we come to discussing those assumptions. But if those assumptions aren't valid, then the answers that we've got into the first 2 parts may simply be wrong. Okay, some more questions. So we might want to ask a specific question. So for example, does the exposure to pollution affect the expelled volume of air? So we might say, can we test whether there is no effect from that variable or whether there isn't an effect from that variable? So how can we perform a statistical hypothesis test to test that question? One thing we might be interested in, particularly with a big data set, is whether there are observations which don't really seem to fit. So we might find that by looking at some plots of the data after we've fitted our model, and we might see that there are some observations which really don't seem to fit in. One other thing is that there might be observations which seem to be having an undue influence in our inference. Okay, so when we fit a model, you'll see that we will end up estimating some parameters in the model. And what we might find is that there's an observation which is having a particular effect on the estimated parameters. So imagine that you've got some data, so this is just going to be some sort of one-dimensional standard regression, and you've got some points like this, and then let's say you've got another point, which is way over here. So in a simple linear regression type model, you're going to want to be fitting a straight line through these points. Now you might well think, looking at what I've drawn over here, that the best straight line through these points looks something like that. But that straight line really doesn't fit this extra point over here very well. So I suspect that what you would get if you tried to fit a straight line by linear regression on the blue points would actually look a bit different. I suspect it would look something like that. And what's happening there is that it's being pulled over towards this outlying point and away from the sort of natural looking straight line through the remaining points. So if you've got something like this, and this point over here is influencing the actual line that you've ended up fitting between the points quite seriously. So it's, you know, all the others, you've got something which is quite nice up over here, and then you've got this one, and that pulls everything away, that pulls the line away from most of the other points. Okay, so that's the sort of thing you might be asking. Is this a problem? Well, if you get something like this, you certainly might want to check whether this point is real. Okay? Because if there's a problem with this observation, then you certainly don't want it to have influenced everything, your estimates of everything else in the way that's been indicated on that board. Okay, and another question is, let's say we have some new patients. Okay, we've fitted our model to our existing patients, and we now have some new patients, and we have these 7 explanatory variables, each of those new patients. Can we predict the volume of air that those patients will expel? And the answer from a good linear model will be yes, we can do a prediction. How good will that prediction be? How accurate will it be? Can we make a confidence interval for the predicted value? So say we have 95% confidence that this patient's amount of air expelled will be between 2 particular values. That's what we would like to be able to do. And with a linear model, we can do this. Okay. So I'm now going to give a general idea of what we mean, what we're going to mean in this course by a linear model. So we're going to start off with a simple linear regression, much like the one that I drew here. So I'm going to get rid of the one I drew here and drew another one which doesn't have this weird outline point. Okay, so we have some x scale, we have some y scale. So xi here is going to be the independent variable, the explanatory or predictor variable. So in fact, it's quite possible that these might be controlled in some experiment. And yi is going to be the measurement, the dependent variable, the thing that we're trying to get a model for. So what we're interested in is how does the x variable influence the value of the y variable. And so we might have some points, and let's say they look something like this. There, something like that. So we get a set of points and we can plot them in an xy plane. Okay? So what we do in simple linear regression is we try to fit a line, which is what we call a best fit line, through these points. Okay? Now obviously, because these points actually do not fit on a straight line, we can't draw a best fit line through these points, but we can try it so that it's as good a fit as possible to the points. So I think a good best fit line through these points that I've just drawn is going to look something like that. Okay, so that's a straight line, so we can write it in the form y is beta naught plus beta 1x. So beta 1 here corresponds to the gradient, or the amount that a unit change in x would make us expect to see y change, and the beta naught term is the intercept, so it's what we would get if the x value was 0. Okay, so we fit a straight line through the points like that. Okay, I'd like to think about this in a slightly different way. Which is that instead we think of a statistical model as starting with a line. So this line is going to look something like this. That's a straight line, and it's a line of the form y is beta naught plus beta 1x. So that's the line. Then our points come along. So our points come along, and let's say these are our x values, so that might be x4, x1, x3, x5, x2. I don't want to have them in, they're not necessarily going to be in order, so that's why I put them in some strange order at the bottom here. And then each one of these points, we expect to get a y value. Now that y value, we expect to be on or near this line. So for x1, we expect our y1 to be somewhere close to this line. So let's make it a little bit below the line. So that's going to be our, what we often call an error term, which is going to be this epsilon I. So that is going to be a random number, which is something a little bit different, gives us something a little bit different from the value which is actually on the line. So we're going to get these epsilons each point. So epsilon 4 might also be a little bit negative, so a little bit below the line. Epsilon 3 might be a little bit positive, so y3 is a little bit above the line. x5 might be a little bit negative. Epsilon 2 might be a little bit positive. So for each one of each value that we have of the explanatory variable x, we get a random value of the dependent variable y, which is the value that we would get on the line plus a perturbation, a random term which gives us something which is slightly different from what we had on the line. Okay, so this point here, for example, would be the point x1, y1. That one is x4, y4, and so on. Okay, so this picture now looks very similar to the picture that we had over here. And what we're really doing over here is we're trying to find a model of this type for the data. So what I did over here was a mechanistic sort of thing. We started off with our x values, and we then produced a y value for each x by saying it's close to the line, but we need to add some sort of perturbation term, which is the epsilon i's for each individual point, which gives us a scatter of points like this. What we're doing over here is we're saying, well, if we assume that the model is of this type, what is the best line that fits for something like this, which fits these data as well as possible? And we'll discuss what as well as possible actually means here. I mean, there's potentially more than one way you might answer that question of what it actually means to fit the data as well as possible. Okay, so epsilon I here is often described as an error term. I'd like you to be a little bit careful about using the word error, because it's not necessarily a measurement error. It's a genuine part of our statistical model. We expect that there will usually be some extra cause of variation which isn't predicted by the explanatory variables. So in a situation like this, the explanatory variable tells us that for x4, we expect the value to be on this line. That's what in the model. However, there is also some variation which is appearing in the y values, which does not come from the explanatory variable x, and that appears as some sort of random variation around the point on the line. And that is what the epsilon I is. Now, it could be a measurement error. You could be doing some experiment in something like physics or chemistry, where there really is a definite value that you expect for each value of the explanatory variable, but you have a measurement error in your experiment, and in that case, the measurement error really would correspond to these epsilon i's. However, it's quite possible that there is no real sense in which the epsilon i's are an error. Okay, so that's just a warning to be a little bit careful about using this word error in terms of what it means. Okay, so we're going to generalise the simple linear regression structure that I've just been describing to allowing us to have more explanatory variables. So the more general idea of a linear model will move from having one explanatory variable we have here, the x's, to potentially having more than one explanatory variable. Obviously, then it's not going to be as easy to draw on a blackboard. Okay, so the most natural generalisation, and one which is going to fit with the motivating example that I gave at the beginning of the lecture, is where instead of having one explanatory variable, as we have here, for each that we think might be predicting each of the values of the dependent variable, we have lots of explanatory variables. So, for example, we could have the volume in the asthma model, and we could have the explanatory variables being the exercise, the pollution exposure, and the pulse rate. Okay, which are all nice continuous variables, so that will fit in well. So, for each observation, if you have that, you're going to have some number of values of the explanatory variables. So let's call the number of explanatory variables we've got R. So the example I just gave is 33. So the 1 might be the pulse rate, 2 might be the pollution, and 3 might be the what's the other one? The exercise. Okay, so for each observation, you have R variables which you know the values of. So those are these x variables. So for observation I, you have xi1 up to xir. And then, for each observation, you have a response, which in the asthma example would be the volume of air expelled. So for patient I, xi1 would be the pulse rate, xi2 would be the amount that they exercised, and xi3 would be the exposure to pollution. Whereas yi would be the volume of air expelled in the experiment. Okay? So you'd have those observations for each I, and you'd have n, so 1 up to I and 1 up to n here means that there are n observations in total, and on each one of them we have the R values of explanatory variables and a single value of the dependent variable. Okay, so if we want to generalise the linear model that we've seen to this sort of setup, we might want to have something like this. So you've got your dependent variable yi would take a value which is some sort of linear combination of the explanatory variables. And these numbers, these betas, which are describing this linear combination of the explanatory variables, these are going to be constant. So these are going to be the same for every patient. Okay, so, and then on the end you have the epsilon I, just as you had before, so this gives you some sort of random term, which is some sort of perturbation about what you get from predicting the values of the, using the explanatory variables. Okay, so you've got a beta naught, which is a constant term, then you add beta 1 times the value of variable 1 for that observation, beta 2 times the value of variable 2 for that observation, and so on. And then you add on, at the end, this random term which could describe some other sources of variation in the experiment. Okay? So, this form here is in two parts. So I'm going to write it again on the board over here. So we've got yi is beta naught plus beta 1 xi1 beta r xir, and then we've got epsilon r. So this is going to be our form for a standard linear model. Can everybody see that chalk colour okay? Okay, so this is in two parts. And the terminology I'm going to use for this, particularly the first part, is going to recur throughout the course. So this part, so i.e. everything except the epsilon I, is called the linear predictor. Okay? So this is the part which gives you a linear combination of the explanatory variables. The coefficients are constant, so they don't depend on which observation you're looking at. So you always have, every term in here is one of these constants, one of these betas, multiplied by the appropriate term of the explanatory variable for that observation. Okay, so the i's, which refer to the observation, appear in x terms, and you're multiplying them by the constants, which are the betas. So that's called the linear predictor. As I say, we'll see linear predictor recurring throughout the course, and it's always going to be something which looks rather like this. And then you have the epsilon I. So I would think of this this as being the random part. So this is the part that the explanatory variables do not predict. Okay? So we have the linear predictor, which is entirely predicted by the explanatory variables, and then the epsilon I, which is not predicted by the explanatory variables. So if I go back to my picture here, which is just one-dimensional, the linear predictor tells us this straight line, and then the random part gives us this fluctuation, these epsilon i's, away from the straight line. Okay, so this is just saying a little bit more about linear predictor. What we're saying, linear predictor gives us this linear combination of the explanatory variables with those coefficients, the betas, which are constant, so they don't vary for the individual observations. It's the x terms which vary for the individual observations. Okay? I've already said that I don't want you to think of the error term as necessarily indicating measurement errors. What you should think of it as variation which is not explained for within the linear predictor. So it could be something which is, you can think of as really essentially random. It could be something which is due to factors which you haven't taken account of. So there might be some missing things, some things you should have measured about the patients, but you didn't. And those would have given you more information, so the epsilons could be connected with those as well. Or, as I said, in certain situations, they really could be measurement errors. Okay, so for the standard linear model, we're going to impose some conditions on these epsilons, these random parts. In fact, we're basically going to assume that they have normal distributions, that the mean is 0, which makes sense. We'd expect the mean to be 0 because we're thinking of them as perturbations away from the linear predictor. That they're independent of each other. And one assumption which is going to be important is that they will all have the same variance. Okay, so I'll come on to the assumptions that we're going to use for the epsilon I proper later. So, the simple linear regression, as in this picture, we're fitting a line to the data. That corresponds to r being equal to 1. If r is equal to 2, then we're fitting a plane through the data. The data now three-dimensional because we have three observations for each, three variables for each observation. We have the two x values, xi1 and xi2, and we have the dependent variable yi. So we have three variables for each observation when r equals 2, so three-dimensional, and we're fitting a plane through the data. If r is larger than that, then we're going into higher dimensions, and so we're actually fitting hyperplanes to the data. So it's easy to visualise in one dimension, it's perhaps a little bit harder to visualise in two dimensions, and depending on how good you are at thinking in higher dimensions, actually visualising it is going to be pretty hard beyond r equals 2. However, the mathematics of the situation all work in essentially the same way. And we'll see more of that as we go through this section. Okay, there's one more twist to what I've just been saying. And to indicate that, I'm going to draw another picture of some potential data. So imagine that you have some data which look something like this. Here's some data points. Okay. So what's going on here? What does it look like is going on here? Well, it looks like for small values of x, you tend to get relatively large values of y. But for large values of x, you also seem to be getting relatively large values of y. Your smaller values of y seem to be in the middle as far as values of x are concerned. Now, we could fit a straight line through these points, and maybe it would actually be the right thing to do. So, probably looks something like that. But there'll be situations where this apparent thing of having the large values of y at the beginning, at the end, sort of small or large values of the x's, and the small values of y and medium values of x's, that might not just be an artifact. It might really be the case that larger values of x tend to give larger values of y, but smaller values of x also tend to give larger values of y. So for something like that, what you probably want to fit is a curve. So if I draw a curve through the data, something like that, that's a reasonably nice smooth curve that I've drawn through the data. And that curve is getting much closer to the individual data points than the straight line I drew earlier. Now, do be aware here that this is not necessarily a good thing. We could be overfitting the data. We might find with more data that in fact the apparent pattern was an artifact, and that with more data we'd see that actually points were just as likely to be near the white line anywhere. So there was no need to fit the curve. So you do need to be a little bit careful here, but sometimes this is an appropriate thing to do. Now, the surprising thing in a course called linear models is that we